chemistry, at its most fundamental level, is the study of matter. And when we say matter, we are talking about the material that makes up the world around us. Whether you are looking at another human, an airplane, or at the Atlantic Ocean, all of these things are made out of something. They are made out of matter, which is a substance that has mass and takes up space, even if we can't directly see it. Like the air around us, we can feel it and breathe it to know it's there, and therefore it has to be made out of something. After extraordinary scientific research and experimentation branching all the way back to the early days of chemistry, we acknowledge the fact that all of the substances around us and within us are based on building blocks called atoms. We're going to talk more about atoms in the next video, but for now we just need to know that atoms are the smallest unit of matter that retains specific properties that we can observe in the natural world. And if we take these properties and organize them, we call them elements. Taking a look at a periodic table, we can see that chemists have classified and organized many elements that make up our universe. The basic idea of an element is that it is a pure substance that cannot be broken down further and still retain its properties, with one atom of an element being the smallest unit that can hold those properties. Let's use carbon and water as an example to help us illustrate this. Carbon is an element that can exist purely in a few different ways. The lead you use to write in your school notebook, called graphite, is made out of pure carbon. If you try to break the graphite into smaller pieces, each smaller piece would still retain the same properties. And even if you broke apart each atom within the structure, all of the atoms would still contain the same properties because they are all carbon atoms. So for this reason, we can say that the graphite within your pencil is made out of the pure element carbon that cannot be broken down any further and still retain its properties. Now we can contrast this example with something like water. If we were to break water down, we would find that the atoms within a water molecule have different properties. And as I am sure you know, water is made out of two different elements, which are hydrogen and oxygen. Breaking apart the atoms of a water molecule, you will find that the properties between hydrogen and oxygen are different. But the hydrogen atoms and the oxygen atom cannot be broken down any further and still retain their properties. So in this scenario, we cannot say that water is an element because it can be broken down into hydrogen and oxygen. Hydrogen and oxygen would be considered elements, as we also see here on the periodic table. Each element that we know of has its own symbol and spot on the periodic table. We learned on the last slide that elements and their atoms have their own unique properties. But a cool thing about these atoms of different elements is that they can chemically interact with each other to form larger molecules, called compounds. Remember that water was made out of atoms from the elements hydrogen and oxygen, and when these atoms bond together in a specific ratio of 1 oxygen atom to 2 hydrogen atoms, it creates the compound that we call water. Compounds have unique names that are tied to specific element combinations at specific ratios. So we call a molecule that has 2 hydrogen atoms and 1 oxygen atom water, and a molecule with 2 hydrogen atoms and 2 oxygen atoms hydrogen peroxide. They are both made out of the same 2 elements, hydrogen and oxygen, but at different ratios, 1 to 2 to 2 to 2. The ratios that make up compounds are fixed, which means if they change, then the compound itself changes. And this happens all the time with chemical reactions, but more on that later. Compounds, along with elements, are also classified as pure substances because they have a uniform composition. 2 or more elements chemically bound together form a compound. So what happens if multiple compounds combine? We call this a mixture. Now we need to be careful with this term because combining compounds to make a mixture is different from combining elements. When elements form a compound, they do so with a chemical change, linking the atoms of one element to the atoms of another in a fixed ratio, giving the structure new unique properties. If 2 compounds come together to form a mixture, they do not chemically change in any way. Instead, they can simply mix and exist next to each other, with each compound retaining their original composition and properties. There is no chemical change that happens. A simple example of this could be sugar water. Water and sugar are both compounds that have their own unique properties, and when you put them together, they create a mixture of the two and spread out next to each other. Neither of them change at the chemical level, which means that it is easy to separate them if needed. There are only 2 types of mixtures that are commonly seen in the chemistry world, called homogeneous and heterogeneous mixtures. A homogeneous mixture is one that has a uniform composition, meaning everything is spread out evenly and therefore has uniform properties. Salt water is an example of a homogeneous mixture. If you put salt in water, it will dissolve into sodium and chloride ions and spread out to be a uniform composition within the solution. This means that if you were to take a random sample of the mixture at any point, you would find roughly the same amount of water, sodium, and chloride within the sample. This results in the salt water having the same properties throughout. An example of a heterogeneous mixture could be a container of muddy water. While there are many compounds contained within the mud, if you let it sit, it will eventually settle at the bottom of the container. So, if we were to take a random sample of this, we could take a collection from the top, which could be mostly water, or a collection from the bottom, which would be less water and more common compounds found within dirt or soil. Now, the cool thing about mixtures is that because the components are not chemically bound to each other and retain their own properties, they can be separated relatively easily. The common idea behind separating mixtures is understanding their properties and using that information to aid the separation. Filtering is a common way to separate some mixtures that don't completely dissolve, like some of the particles in the mud here, but that is only one method. Other methods can be used, like separating a magnetic substance from a non-magnetic substance via a magnet, distillation or evaporation of liquids with different boiling points, paper chromatography, crystallization, and others. Your teacher should go over these methods in detail with you, but for now, always remember that these substances within mixtures can be separated by physical means because they are not chemically bound together and therefore still retain their own properties. Another important aspect of studying and understanding matter is learning information about its state. There are 3 general states of matter in which all substances can exist, which are solid, liquid, and gas. Take a look around the world and you can see examples of these all over the place. The water you drink is a liquid, the air you breathe is a gas, and the paper you are currently writing your notes on is a solid. Let's stick with water as our sample substance to carry through the rest of the slide. Solid water, or ice, can turn into liquid water through the process of melting, and liquid water can turn into gaseous water by evaporating. We can also go the other way and say that gaseous water vapor can condense into liquid water, and liquid water can then freeze into solid ice. But why does this happen? What makes the same liquid water molecules freeze or solidify? That is where the kinetic molecular theory comes in, along with other things like atmospheric pressure, but we'll talk about that in a later video. The term kinetic describes the energy an object has due to its motion, and in this case, the object is a molecule, which is where we get the molecular part from. The kinetic molecular theory of matter is a model that explains the behavior of matter. It states that all matter is made out of small particles that are in random motion and have space between them. Particles are attracted to each other, and so they tend to pull together, and can move apart only if they have enough kinetic energy to overcome the force of attraction. So if we have solid ice and add energy to it by heating it up, the molecules will vibrate and move faster until some of them start to break off and are able to freely move around in a liquid state. And then we can continue to add energy until those liquid water molecules move so much that they can break off into a gaseous state. The term endothermic describes a change of state from more compact to less compact because energy is taken up for the physical change to take place. And exothermic describes when energy is released or taken away from the substance to cause the state change. 2 other important state changes to know about are sublimation and deposition. Sublimation occurs when a solid state changes directly into a gas, and deposition occurs when a gas state changes directly into a solid. Both processes skip the liquid phase and therefore have a larger exo and endothermic swing in energy compared to just condensing or melting. We have talked a lot about energy, heat, and temperature, but have yet to put a solid definition on how we measure it. In chemistry, we often measure temperature, which in equations is written as a capital T, using units called Kelvin. The unit for Kelvin is represented with a capital K and describes the average kinetic energy of particles. This is one of 7 base units of the International System of Units, abbreviated SI, that are widely accepted and used by scientists all over the world. Kelvin measures the temperature of a substance on an absolute scale, meaning there are only positive measurements within the system and the lowest the scale can go is 0. This differs from using the Celsius scale because temperature in Celsius can go into the negatives. So what does this actually mean? With a Kelvin temperature of 0, which we call absolute 0, means that there is absolutely no kinetic energy between the particles being measured, meaning that there is no movement at all between the particles and therefore has no collisions and no heat. This is the absolute coldest measurement that particles can take, completely void of all heat and movement. Contrast that to 0 degrees Celsius, which is the temperature at which liquid water freezes into ice. We would say that this is cold, but the molecules in the ice still contain kinetic energy and are moving and vibrating next to each other in the solid state. And this goes for all other solids as well. There is always a bit of movement between particles within a solid state. Scientists have come close to reaching absolute zero, but have never actually achieved it because the massive amount of energy needed to be removed to eliminate all heat from an object. When comparing the Kelvin scale to the centigrade scale, they increase by a 1-to-1 equivalent, meaning that a temperature change of 1 Kelvin is equal to a temperature change of 1 degree Celsius. The difference again is the scale. And to convert between the two, we can use the conversion of 0 degrees Celsius is equal to 273.15 Kelvin. So we can calculate that water boils at 100 degrees Celsius, which is 373.5 Kelvin, and absolute zero would be written as 0 Kelvin or negative 273.15 Celsius. Make sure to know how to convert between the two by either adding or subtracting the value 273.15.